Okay, so today's lesson is going to move on to our second gas law, which is called Charles' Law. So this is again looking at two different variables for measuring gas while keeping the third variable as well. So when I say third variable, in this case, it's going to be the pressure is going to be kept constant, but we can also assume that the amount of gas is also kept constant. Okay. So what happens when we play around with temperature and volume? How do they relate to one another? So at constant pressure, in a container that can expand, so this is important to know, the container is able to increase and decrease in size. As the temperature of a gas increases, the volume also increases. So if we think about what happens when we add heat to a gas, we know that it increases the speed or the kinetic energy of the particles. It also causes them to move further apart. They're going to expand further away from each other. So as that temperature increases, the gas particles move further apart, which makes for a larger volume. The relationship between temperature and volume is what we call a direct relationship. So our last relationship was inversely proportional. In Boyle's law, when volume increases, pressure decreases, and vice versa. Whereas a direct relationship means that when one increases, the other one also increases, and vice versa. When one decreases, the other decreases. So direct, they do the same thing. Inverse, they do opposite things. So in other words, as the temperature increases, the volume also will increase proportionately. Whoops. Okay, so here's a graph of volume versus temperature. And you can see that as volume increases, temperature also increases, and this is a nice linear relationship here. Whereas remember with volume and pressure, we got a negative slope on our graph, and it was more of a curved line, right? The slope changed. Here it is a nice linear progression. So other gases would have different slopes, but they would all be a positive linear relationship like that. It would just, the slope of the line may be different. So let's kind of take a look at this situation. So we've got our set amount of gas, okay, so the number of gas particles is the same in both containers. The pressure is constant, so the pressure is staying the same throughout the experiment. And we've got a source of heat here, okay? So as we increase, so this is supposed to, the larger flame is representing a higher temperature, and you can see the temperature is recorded here on the side. So we've got a lower temperature on the left, a higher temperature on the right. Okay, so as we increase the temperature, this is like that movable piston I talked about in the last lesson. This is able to push up and push down to change the volume of the container. So as you heat the sample of gas, the particles move further apart from one another, and they push that piston up, increasing the space inside the container, so making a larger volume. So an increase in temperature gives an increase in volume. The lower temperature has a smaller volume. Okay, so this is named after Jacques Charles, and he used this relationship, and he showed it like this. So volume is equal to K times T, where K is a constant that T is multiplied by. So he rearranged that formula to give this relationship. The constant is equal to the volume divided by the temperature. So volume 1 divided by temperature 1. Okay, so if you change the temperature or volume, you still get that same constant value. So just like we saw in Boyle's law, within the same experiment, as you changed the values for in your data table, you always ended up with the same value for K. The same type of experiment was done by Charles, and he found that when he divided volume by temperature in each in each trial that he did, he would get the same value for K. Okay, so V1 divided by T1 equals K, and so does V2 divided by T2. So your second set of volume and temperature values also give you the same. And you can just keep going. You could sub in a third set of volume and temperature and still equal K. So because of that, if K equals V1 divided by, oops, that's not T1, it should be TI, it should be T1. And K also equals V2 divided by T2. Then, therefore, we can set these two equal to one another. Volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. So just like we did with Boyle's law, if we know 3 of these 4 values, we can solve for the 4th one using this relationship. So Charles' law simply states, as the temperature of a gas increases, the volume increases proportionally if the pressure and amount of gas are not changed. So as long as those two things stay constant throughout, an increase in temperature causes an increase in volume. So if you change the temperature of a gas or its volume, the new temperature or new volume can be worked out with the equation for Charles' law. So let's do some problems so you can see how this works. Now, the important thing here is that the temperature must be in kelvins. So we can't use degrees Celsius in this formula. The relationship does not hold true with using degrees Celsius. It must be in Kelvin. The volume unit doesn't matter. It can be in any volume unit, but the temperature unit does. So in our last Boyle's law problems, you could use any volume unit and any pressure unit as long as you stayed consistent throughout. Okay, for Charles' law, volume units, again, use whatever is given in the question, just be consistent, but temperature must be in Kelvin. Okay, so let's try a few problems so you can see how this works. So this says the gas inside a closed cylinder with a movable piston is heated to 315 degrees Celsius. If the volume of the gas was 0.3 liters when the temperature was 25 degrees Celsius, find the volume when the temperature is 315 degrees Celsius. So let's do the same kind of thing that we did with Boyle's law. Let's make ourselves a list along the side and identify our variables. And then that helps us plug into the formula afterwards. Okay, so if the volume of a gas was 0.3 liters, okay, so we're assuming that we're starting at a volume of 0.3 liters when the temperature was 25 degrees Celsius. Okay, so again, just like in Boyle's law, what you define as 1 and 2 isn't very important as long as they're paired correctly. Okay, so it's the 25 degrees Celsius goes with the 0.3 liters. So we've got them as a pair together. Find the volume, that's what we don't know, when the temperature is 315 degrees Celsius. Okay, so right away we can see that our temperatures are in degrees Celsius. We can't work with that. We have to convert to Kelvin. So if you remember back, to convert to Kelvin, what you do is you add 273 to convert to Kelvin. So 25 plus 273 is 298 Kelvin, and 315 plus 273 is 588 Kelvin. So now that we have that, let's plug in what we know, and we can cross multiply to solve for what we don't know. Okay, so V1 is 0.3. T1 is 298. V2, we don't know, so I'm just going to leave it as V2. And T2 is 588. Okay, so what you can do then is you can cross multiply to solve for V2. You can also rearrange your formula first, and that's another approach. Okay, so that's going to give me 588 times 0.3 is going to give me 176.4. And then I'm going to get 298 times V2. So to isolate V2, I'm going to divide by 298 on both sides. Okay, so V2 will equal 176.4 divided by 298, which is 0.59. And I'm going to use the same volume unit that I was given, which is liters. Okay, so you always just want to double check that this makes sense. So we started at a lower temperature and we increased our temperature. So if we're increasing our temperature, we should also be increasing our volume. And we can see that that is true. We started at 0.3 and we ended at 0.59. So what you can see as well is it's a proportional increase. So the temperature almost doubles and the volume almost doubles if you look at your numbers. Let's try another one. A gas that has an initial volume of 3.42 liters at a temperature of 215 Kelvin is in a container where the volume increases to 6.55 liters. What is the new temperature of the gas? So again, I'm going to list everything down the side. Okay, so an initial volume, so that's where we're starting, 3.42 liters at a temperature of 215 Kelvin, and the volume increases to 6.55 liters. What's the new temperature? So we can plug in to our formula. So V1 goes here, divided by T1 equals V2 divided by T2. So let's cross multiply. We get 3.42 times T2, and 215 times 6.55 is 1,408.25. So now we want to isolate T2, so we're going to divide by 3.42 on both sides, and we get that T2 is equal to 411.77 Kelvin. All right, so the last example we'll do, and then you can work on the Charles Law questions, that's worksheet 4, is a gas that has an initial temperature of 50 degrees Celsius is heated to 150 degrees Celsius. If the final volume is 2.75 liters, what was the initial volume? So let's write that all down. Okay, so initial temperature is 50 degrees Celsius. Let's change that to Kelvin right away so we don't forget. So it becomes 323 and is heated to 150. So that's our final temperature, or our T2. We're going to change that to Kelvin so we don't forget. That becomes 423 Kelvin. The final volume, so that's going to be V2, is 2.75 liters. What is the initial volume? Okay, so let's fill in what we know. V1 divided by T1 equals V2 divided by T2. If I cross multiply, I get 423 times V1, 2.75 times 323 is 888.25. Now I'm going to divide by 423 on both sides to get V1 is equal to 2.1 liters. Okay, so these are fairly simple calculations. The most important part is making sure to identify your variables correctly, and then it's just a matter of solving for the unknown variable. So go ahead and work on worksheet 4 to practice this skill.